temperature system designs. The focus of this webinar, however, will be closed-loop, low-temperature applications using geothermal or geoheat pumps. Just a point of information, the direct use bullet under low temperature in this slide is a very small percentage of the industry where a low-temperature resource is used to heat, say, pools or buildings, such as what you might encounter at the Esalen Institute near Big Sur or north of us in Klamath Falls, Oregon. Because of the warmer temperatures, the resource is used directly instead of coupling with a geoheat pump. There is a long and well-documented history of geothermal energy that gave way to the development of the modern geoheat pump industry. One of the first geothermal power plants is shown here, dating 1904. Prince Pio Gennaro Conti invented the first geothermal power plant in the Larderello dry steam fields in Tuscany, Italy. But the development of geothermal resources had already begun in California prior to this first in Italy. While the geysers had already been established as a spa destination in 1852, in 1862, Sam Brannan poured $500,000 into an extravagant development dubbed Calistoga. After 150 years, Calistoga continues to be a destination for those interested in hot springs and, of course, good wine. The previous first are examples of the direct use low-temperature geothermal resource that I mentioned in the first slide. The use of the geothermal heat pump did not start for another 86 years until in 1948, when the first ground source heat pump was introduced by Professor Carl Nielsen at Ohio State University. Same year, the first commercial application of an open loop system used a water well was pioneered. The water source heat pump technology had been around for a while, and the challenge was how to efficiently accommodate the ground heat exchange with existing technology. Was a heat exchange with a closed loop system or heat exchange with the water well system? For water heat pumps to become geoheat pumps, the operating conditions must be modified to accommodate extended range operation for ground coupling. This means that their range of operation is extended from a water source application of, say, 50 to 85 degrees entering water temperature. And when I speak of entering water temperature, I mean entering water temperature to the heat pump. To a range of 25 to 110 degree entering water temperature, which is more conducive to coupling with a ground loop or a groundwater, or commonly referred to open loop system. Extended range is accomplished by essentially increasing the size of both the coax heat exchanger and air coil fairly significantly. Keep in mind that both must be matched due to the refrigerant charge balance. Pump controls tend to change to allow for very cold entering water temperatures in some cases, and the occasional return air being a bit lower, which is rare in most commercial applications. So most manufacturers utilize both refrigerant low pressure and entering water temperature low temp protections or limit devices. Another difference is water and refrigerant lines could sweat with the within heat pump cabinet and are insulated along with the entire coax heat exchanger, and that's all within the heat pump cabinet. Finally, all geoheat pumps now utilize thermal expansion valves, or TXVs. So you can see here on your slide that although a lot of activity was going in the Midwest and in Canada in the late 70s and early 80s, for some reason this technology is just starting to catch on here in California, and it's another 40 years into the future. This has always been one of the challenges of our industry since geoheat pump development back in the 40s. What is the term? These are all talking about the same system, a geoheat pump and some type of ground or water heat exchange. The following series of slides will give you a visual perspective on how the technology works. from the sun, our astrophysical resource, warms the Earth and helps to maintain constant Earth temperatures, depending somewhat on geographical location and depth. There is some geothermal energy contributing from the Earth's core, which radiates outward to the Earth's surface or crust. But in most locations, this contribution to maintaining the shallow Earth's crust temperature is very small. The geophysical properties are key to providing a properly sized ground loop for coupling to geoheat pumps. There are 4 different circuits that we typically think about with geoheat pump operation. They're listed here. First, a distribution circuit. Next, a refrigerant circuit, which is basically the thermodynamic cycle that governs a heat pump. Ground loop circuit, and then a hot water circuit. Every heat pump has included in its cabinet basically 2 heat exchangers. One exchanger transfers the heat to and from the ground loop water circuit to the refrigerant. A second heat exchanger transfers the heat to and from the refrigerant to the building's air or water distribution system. The hot water circuit number 4 is typically only applicable to residential applications and is mentioned here as another option to give homeowners functionality from their geoheat pump unit. What we're going to start with is looking at the refrigerant circuit. Let's start by looking at the thermodynamic cycle of a geoheat pump in heating mode. Air to water heat exchanger in the geoheat pump, vapor, sure, energy to the air, causing the refrigerant to change state from vapor to liquid, depicted here in red. This liquid is passed through the bypass valve, then the expansion valve, where heat is absorbed and the refrigerant again changes state at the ground loop heat exchanger. Let me back up here. The cold liquid is passed through the water refrigerant heat exchanger at the ground loop, where heat is absorbed and the refrigerant again changes state from cold liquid to cold vapor. The refrigerant valve then directs the cold vapor through the compressor where work is done on the refrigerant to heat the refrigerant to vapor, and the cycle starts all over again. Next, let's look at the geoheat pump operation and cooling modes, starting with the light blue. You'll see the refrigerant circuit is reversed. At the air-water exchanger in the geoheat pump, cold liquid absorbs heat from the airstream, causing the refrigerant to change state. This cold vapor is then circulated to the compressor. Work is done heating the vapor. The reversing valve then directs this hot vapor to the water refrigerant heat exchanger, where the hot vapor rejects heat to the ground loop. As heat is rejected, the hot vapor changes to hot liquid. It is then routed through the bypass valve and the expansion valve, where the hot liquid is cooled and the cycle starts all over again. A very simple example of a geoheat pump system for single-family residents, or it could be equally applicable to, say, an individual classroom application. The only difference being that we would remove the preheat tank and hot water portion of the system. The 3 areas to focus on in this simple diagram are first, the heat pump, depicted by number 1, 2, the pump that circulates water between the heat pump and the ground loop, and 3, the ground loop itself. In this example, we are showing a vertical closed-loop ground heat exchanger. We use the constant temperature of the Earth to move heat in the most positive direction for transfer based on the needs of the building. In this example, it is summer, and we move the heat from the building to the earth. Here, we reverse the process, taking the heat out of the earth and put it back into the house or classroom. As in the previous slides, the ground loop alternates between evaporator and condenser depending upon the season. Important to note here that for geo heat pump system designs, a balance between heating and cooling is needed to minimize ground loop size and cost. A lot of calls from central plant owners who believe that the best way to utilize this new technology is to remove their cooling towers and just put in a ground loop. Well, that's fine, but we must also have a way to use the heat rejected at a later time, either stored in the earth for heating in the winter or immediately in an energy recovery type application such as domestic hot water, which is typically a year-round load. We'll see here there are many different types and sizes of geo heat pumps. Just the conventional HVAC system equipment, it is very important to apply the correct equipment to the correct application. On this example of equipment, you'll see split equipment, which would replace a more common air source heat pump, air handler configuration in a home, office, or classroom. You have upflow and downflow equipment, water, air, all in one package. You have console and horizontal packaged equipment, which you might find in, say, portable housing or apartment complex or a hotel motel. And then we do have very large sizes of equipment that might go on a rooftop and support larger commercial or industrial applications. Here's a look at the inner workings or guts, if you will, of the water-to-air heat pump. You will see it isn't all that different from other types of mechanical equipment and that it is of a similar footprint. Here you see some of the components that you're used to seeing with more conventional equipment. You have different blower types, obviously an air coil. You have your compressor, a lot of new compressor technologies, different types. All of these are within the same cabinet that is really, like I said before, not much different than what you would expect with an air source air conditioner or even a furnace box. And this option for desuperheater, or what is often also referred to as hot water generator, is mainly for residential applications whereby during air conditioning mode, a portion of the heat which is normally rejected to the ground loop may be instead diverted to a domestic hot water system. Keep in mind that in the winter, the same desuperheater feature uses a portion of the geo heat pump capacity to heat the building and also the hot water. It is important to select the heat pump properly and to account for the total heating requirement of the building. So let's talk a little bit about the ground loop. This seems to be the biggest mystery to most design engineers, and so we'll be focusing quite a bit of time on this particular element of a full geothermal heat pump system design. There are a lot of design variables that need to be determined by the design engineer to properly size the ground loop. For example, the ground temperature, ground heat transfer properties, sizes and materials, fluids, and grout if a drilled or bored heat exchanger is selected. A decision is to be made about design temperatures. In warm regions, we typically design for entering water temperatures, again, that's in water to the heat pump, of 45 to 90 degrees Fahrenheit. In other regions, we are typically designing for a lower entering water temperature of 35 to perhaps 85 degrees Fahrenheit. This is done to keep the ground loop size within reason for construction budget. It does, however, require that an approved antifreeze solution be added to the water loop to prevent it from freezing during long periods of heating in the winter. Laying out the system requires knowledge of the requirements for proper flushing and purging the ground loop, in addition to understanding the impact of the ground loop and piping design on pumping energy. No other information available at the beginning of a project There are two places to find information which may be helpful to the design engineer in estimating the deep earth temperatures for their project. This chart depicts the groundwater temperature map for the United States, and while it is very much an overview of water temperatures, it does give the designer a good place to start. Another source is looking online at different weather data sources. The average annual air temperature of a particular location may also be used. And typically, you will find that those two numbers are very, very close. California's geology is quite diverse. Rules of thumb that are typically given in design courses and manuals are always consistent in California. In fact, some of us like to refer to these rules as rules of thumb. Keep in mind that a lot of the original research for geo-heat pump systems was done in Oklahoma. That research was actually done back in the late 70s, as was shown in that previous slide. Geology in Oklahoma is pretty consistent and much different from most places in California. In California, we have sandy beachfront, rocky mountains, great valleys, and we have several locations of hot geothermal activity that would not be conducive to geo-heat pump systems. They would actually be more suited to direct use applications like we discussed earlier in the presentation. We have soil conditions ranging from wet or dry sand to metamorphic rock, and have temperature ranges from 42 degrees in the Sierras to 72 degrees along the Southern California coastline. And inland and some of the desert regions, you might even be up into the high 70s. The current industry materials for ground loop in most states is plastic pipe, specifically high-density polyethylene pipe and cross-linked polyethylene or PEX-A pipe. What isn't highly conductive, it is used due to its performance over time. When forming design calculations for the ground heat exchanger, the good designers quickly realized that the greatest resistance to the heat transfer process is the earth itself. Install highly conductive pipe will not significantly improve the ground loop performance. The history of polyethylene pipe started with an obsession of the hula hoop. Well, I'm just going to take this as truth. Moderator Sean provided me with this slide. What I share with you is that the specification for piping materials for the ground loop has changed at least 3 times since 1948. There was trial and error resulting in failures in the past. The geopump industry learned from its early mistakes and has converged on this particular type of plastic pipe because it is fused. It has no mechanical fittings, and because it has great reliability when installed properly. Here's a photo of the high-density polyethylene pipe as it is typically provided to a project site. It's typically provided on pallets, and it is typically ordered to the length required. And if drew board, the loop is typically specified and comes pre-configured with the U-bend fused at the end of the pipe. And this is the part that would be inserted into the borehole. We'll get into some more pictures here just shortly. Early, the fusion of the pipe connection for direct burial applications reduces the opportunity for leaks in the ground loop. There are different types of fused connections approved for ground loop systems, circuit, butt, and electrofusion, for example. Each type of connection requires different tools. Some connections, such as socket, are more cost-effective and easier to install on smaller diameter pipe, while the larger diameter pipe work requires butt or electrofusion. Here's an example of the PEX-A product. One of the products offered is a double U-bend system. Realize that the ground loop capacity does not double with 2 pipes in the borehole. And calculations must be performed to determine just how much additional capacity the second U-bend yields for the system being designed. This type was approved by the International Ground Source Heat Pump Association in 2009. Its properties are similar to HDPE, and for vertical loops shown here, there's a specific U-bend pre-installed by the manufacturer to keep with the industry theme of no mechanical fittings below ground. There are some very basic examples of different ground loop configurations. These configurations are applicable to both residential and non-residential applications. Read from left to right and top to bottom, we have a horizontal loop, a vertical loop, pond or surface water loop, and open loop or water well type application. An example of a vertical loop being installed on the left and looks diagrammatically on the right as it goes into the earth. The driller drills a borehole vertically down into the earth. Then a prefabricated U-bend loop, which you'll see in the bottom left photo, is put down into the borehole to the depth specified by the design engineer. Finally, the borehole is filled with grout from the bottom of the borehole all the way to the top at grade. There are guidelines noted in this slide to assist the designer in laying out their ground loop system. A recommendation of a maximum of 12 boreholes connected to a single runout, or what I like to call a subheader on larger systems, is recommended. This is mainly done to ensure that the ground loop or portions of the ground loop can be properly flushed of air and debris prior to the connection to the building systems. Runout at 4 to 5 feet below grade is driven mainly by trench safety protocols that say if workers are doing work in trenches, that the trenches cannot be deeper than 5 feet without the addition of shoring. Obviously, that's an OSHA requirement, and we are always conscious about things that add cost to projects. So if you have a particular project where you have an opportunity to go in and put in a ground loop system, whether trenched or drilled, where a lot of earth movement is done, you could actually make these runouts much deeper than the 4 or 5 feet listed in this slide. Again, the photo on the left shows what the factory fused U-bend looks like before insertion into the borehole. The photo on the right is showing the borehole before it is grouted. Ground requirements vary from state to state. In California, it is required that all boreholes be grouted from the bottom of the borehole top to ensure that the borehole is properly sealed. The concern is that if the borehole is not properly sealed, it may act as a conduit between aquifers, potentially contaminating the groundwater. In California, a large percentage of our drinking water comes from these underground aquifers. Use requirement to our advantage as design engineers comes in the form of specifying the grout properties that result in the best performing system weighing both the heat transfer properties against the grout and drilling costs. They're specifying a super high conductivity grout if it costs too much and your local driller has no ability to pump it. Previously, we discussed the great diversity of soil properties in California. On larger projects, those in the 20 to 25 ton range or larger, it's a good idea to have a thermal conductivity test performed. This test is applied only to vertical loop systems. I've seen in some cases where engineers are specifying thermal conductivity tests for horizontal, trenched, or loop systems, and I would caution you to understand what is behind this test, because what we are counting on here is a deep earth temperature, and there's a lot of impact to horizontal systems that you'll see in a slide further down this presentation that may cause this test to not be interpreted correctly. So for the conductivity test, it is really the best way to determine drilling conditions for project budgeting, the deep earth temperature, and the soil conductivity. And from this information, a thermal diffusivity may be calculated. Here's an example of what the test data would look like, and an excerpt from a test report that you might receive as part of this process. It goes like this. A hole is drilled to the depth anticipated for the system design. The ground loop pipe is inserted and the borehole is grouted from the bottom of the borehole to the top. The pipe is filled with water if it already doesn't have water in it, and the test borehole is allowed to rest for 3 to 5 days. This is maybe because we want to make sure any heat of hydration or anything that might be tied to the drilling process is not allowed to give false readings in the thermal conductivity test results. An apparatus like the one shown in the previous slide is connected to the test loop. The test loop should run a minimum of 36 hours and really no longer than 48. The aeration pump is turned on and water is circulated through the test loop. Data is collected every 5 or 10 minutes. The water temperature is measured 30 minutes or so that a deep earth temperature may be determined. After this, a heat source is connected to the water, and the data log measures the temperature at both the inlet and the outlet of the test loop. After 10 hours, the system becomes stable, and the slope of the logarithmic plot time versus temperature is used to determine the conductivity of the formation. So basically, the slope of this line on the chart ends up being the conductivity of the formation. Note again that I'm saying it is the conductivity of the formation. It is not, doesn't have anything to do with the grout or the pipe. It has to do with the response of the formation to the test. And just as another reference, earlier in the first slide, I gave reference to ASHRAE HVAC Applications Chapter 34. In the chapter, you will also find information about this thermal conductivity testing process.
And if I can just interrupt for a second, allow you to maybe take a sip of water. I just wanted to remind everybody, all the viewers, that if at any time you have a question or a comment, you can go to the top of your screen and a small toolbar should drop down. Within that toolbar, you'll see a participant, a chat. If you click on either one of those, it'll open up a side window, a smaller window that you can, with the chat feature, insert and type your question into that box at the bottom of that window. Or view the participants list. You'll see in the lower left there's a raise hand feature. That raise hand feature will put a hand up next to your name and be able to unmute you and have you ask your question. During that time, feel free to use the chat or the participants raise hand feature. And we'll have an open question session at the end of the presentation, being follow-up comments or questions. Thank you.
Okay, just to wrap up the discussion on thermal conductivity testing, note the results, test results you might receive would look like this. In the drill log listed in this report, you'll see that there is information about each formation, its depth, and type. There's also information on the deep earth temperature from this and the data shown previously. The soil properties may be determined from that data. This information is used by design engineers to calculate the ground loop size for a home, a building, or an entire campus. This chart is a good segue into our next topic, which is horizontal loop systems. If you look at this chart, you'll notice that there are 3 different colored lines. Each line represents a different depth below the Earth's surface, and this is obviously for a particular location. If at the black line, which represents 2 feet down, you'll notice that the temperature varies from around 42 degrees in the February and March time frame and warms up to about 82 degrees in the fall. If you look at the red line, which is the 12-foot depth mark, you will see that this variation is much narrower in the 58 to about 72 degree range. The point of this slide is to inform you that when horizontal closed-loop systems are designed, whether they are trenched or bored, the impact of the outside air temperature on the shallower Earth temperature can have a significant impact on final loop size. We no longer have the advantage of a constant Earth temperature, as is what we were counting on for that thermal conductivity test. We now have a variable to consider, which we might call the constant varying Earth temperature. Here's an example of a horizontal directionally drilled system. With this type of drilling or boring equipment, we now have a way to get horizontal loop pipe below grade into deeper soil than might be possible with a trench system. Also less intrusive to the landscape than a horizontal trench system. This technology is just starting to make headway into the California marketplace. Diagram gives sectional views of how this horizontal directional drilling type of ground loop is installed. The bore is either drilled down at an angle and then horizontally below the surface, or another case would be the horizontal loop is drilled down horizontally and then put up at a specified distance from the original entry into the earth so that the loop can be pulled back from one end through to the other. First case is more like a vertical loop system. Case actually punches through the earth in 2 places. It is recommended in most cases that these systems be fully grouted. Directional drilling is not the only method for installing horizontal closed-loop systems. The trend up until now was basically provide a trench solution. This is much more practical and cost-effective in locations where there's a lot of land, for example, lawn, pasture, parking lots, and playing fields. Recently, the HDD has been given more attention because, when I say HDD, I mean horizontal directional drilling. It's been given more attention because of its ability to put the ground loop under buildings or ponds or landscaping. And again, it also has the opportunity to reduce impact to the project site. A view of another horizontal loop system called a slinky. It's to get more pipe into the ground in fewer trenches. Caution is given to the design engineer to carefully consider the application of this type of ground loop. Just like the U-bend application, twice or 3 times the amount of pipe in a borehole or trench does not increase the ground loop capacity proportionally. Calculations accounting for the pipe diameter, the depth, and the soil type must be performed. For systems that are cooling dominated, the amount of heat rejected by the home or building may cause the soil to dry out with this particular configuration. This is heat transfer and could lead to a hot loop. Example of a pond loop, or what is often called a surface water loop. This is a local California example of a pond or surface water loop system in Sonoma County. It has been in operation for less than 6 months. In the photo, you will see the high-density polyethylene pipe being prepared for unrolling into a slinky configuration for placement in the pond. Next slide shows the slinky loop unrolled and lashed to a PVC frame for distributing the piping out into the pond prior to sinking. It's a way to go out and make sure that pipe is not going to be laying on top of the neck guide to it. You'll see that here in the next picture. Here there are about let's see, there's about 16 of these slinky loops left together on this PVC frame. And basically, at this point, what you see is if you're a loop contractor or mechanical contractor that's going to be installing these types of systems, it's totally acceptable to procure a rowboat because you're going to need it to get that pond out into the middle of the pond and get it coordinated and organized for sinking. The next step after this would be to, like I said previously, fill the loop up with water and allow it to sink. Let me go back. This system also uses cement blocks to weight the system down to the bottom of the pond. In most pond applications, the pipe is kept above the bottom of the pond, so sediment has less opportunity to foul the pipe. In this particular design, the idea was that it would be a hybrid slinky/pond loop heat exchanger that was sunk directly to the bottom of the pond to try and take advantage of the available conductive heat transfer with the bottom of the pond surface, in addition to the convective heat transfer, which is basically the feature of these different surface water systems, including the pond type. Providing heat transfer between a pond and a building loop system is to use a plate heat exchanger. Obviously, there would need to be a reasonable location to secure this heat exchanger in the pond, such as under a diving platform or tied to a pier. Water quality is something that has only recently started getting more attention in this geoheat pump industry. Systems that are installed in warmer regions, only the local tap water is typically used to fill the closed-loop system. The point is that the quality of water can vary significantly, and the use of various pipe materials above ground in the building may require some type of water treatment for the circulating ground loop water. It is important to be aware of the equipment manufacturer's water quality requirements, such as those depicted here, and also of the local groundwater regulations. Before any ground heat exchanger system of any type is installed, the local authority having jurisdiction, which in California is typically the county, must be consulted. Connecting a few loops together for a residential system or hundreds of loops together for a school, it is important to think about how all the loops should be connected or headed into a main pipe for pumping to the heat pumps inside the building. A header is recommended to gradually increase or decrease the system pipe size to match the system flow rate. In some cases, these headers can be purchased prefabricated for closed head applications. Usually, these reducing headers are fused in the trenches. The return header solution is the most popular configuration employed by design engineers and contractors because when installed and flushed properly, the piping design ensures that there is equal pressure drop and heat transfer for each individual ground loop. This is not the only solution. A direct return solution may be employed if less than 30% of the ground loop head loss occurs in the longest header. This is per Cavan Rafferty's 1997 edition of the Ground Source Heat Pump Design Geothermal Systems for Commercial and Institutional Buildings. And just so you know what I'm talking about, a picture of that design guide. The design guide should be on every design engineer's bookshelf. It was first published in 1997, as I mentioned previously, and is currently being updated and revised by ASHRAE. It is anticipated that the second edition could be ready as early as the fall of 2014. While the previous Blue Book is focused on commercial applications, it does have a lot of good information relevant to any ground loop system or building application. For residential, and light commercial, it is also recommended that this design guide, which is shown on your screen here, to the Design Engineers Library. It is published by the International Ground Source Heat Pump Association. Moving on, once the ground loop installed, we can move inside to the building. For the Geo heat pump system, all the items listed above need to be installed and properly integrated. We have the Geo heat pump, we have a pump flow center, we have a hose kit or piping. Sometimes we need to have valves and include those hose kits. In some locations, the heat pumps are ordered with auxiliary heating, and typically this is done in colder regions where making the ground loop for the total heating requirement of the building or home would maybe break the budget, and so strip heat or auxiliary heat is often provided. And mostly I believe this is in residential type applications. Then of course we have the thermostat or controls, and all of that ties to our loop or water source. We need to be able to circulate water between the ground loop and the Geo heat pumps in the building. For smaller systems, flow centers are popular and provide integrated three-way valves so that the flow center may be used to flush and purge both the side of the system and the building side of the system. Flow centers are provided by different heat pump manufacturers and pump manufacturers alike. Flushing filling is very important. For small projects, a flow cart may be purchased or assembled. Larger systems, a more customized version of a traditional flush cart with, of course, large water storage and larger pumping horsepower will be required. The goal of flushing is to create a minimum flow velocity of 2 feet per second in each pipe so that any debris from the construction process may be dislodged and removed from the ground or from the pipe. We don't want any sand or pine needles or pipe shavings circulated through what will eventually be our closed loop system. This can cause problems not only for the heat pump coil, but the pumps and any biological type material that's left in the closed loop system could decay and cause problems for the water quality. Here's an example of a larger pumping system for a commercial project. A single pump is used to move water between the ground loop and the heat pumps. You can pumps down here in the bottom right-hand corner of your screen. Second pump is staged on only in response to ground loop temperature so as to maintain a predetermined range of temperatures to each heat pump in the building. The system is the primary loop. Pump is provided, not shown in this picture, at each heat pump, and typically these are installed within the heat pump cabinet, and circulators are used instead of, say, a two-way valve, which would typically be designed for two-pipe systems to larger variable speed pumps. Basically what happens is any time that the compressor is engaged at the heat pump for either heating or cooling, that small circulator pump would be turned on as well to pull the warmer or cooler water from the primary loop to the heat pump on demand. One of Schraper's, Kirk Mesker, coined this type of piping system one pipe, but in reality it's basically a primary secondary pumping system. Okay, so let's do a quick review of the entire process, looking at a vertical loop installation as an example. First, we perform a visual inspection of the pipe that is delivered to the project site to make sure it's not damaged. This is a recommendation. Next, we perform a pressure test on the pipe to make sure that it will not leak before it's put into the borehole. That some pipe may be delivered to the project site already pressurized. First pressure test required by ICSPA, and again ICSPA stands for the International Ground Source Heat Pump Association, which is the current industry standard. Next, drill the borehole. Insert the pipe into the borehole and grout it from the bottom of the borehole all the way to the top. Notice I've said that 4 or 5 times through the course of this presentation. Feed header pipe to the ground loops and thoroughly flush. Next, perform a pressure test on the ground loop to make sure there are no leaks. This is also required by EXPA. In the geoheat pump, the pump or flow center and controls. Purge and pressure test the inside piping system. Canal loop to the building loop. And finally, add antifreeze water treatment if needed and allowed. If geothermal heat pumps are so great, then why aren't there more installations in California? Good question. As you saw in the earlier slides, there was a lot of geothermal heat pump activity in the Midwest, 40 years ago. And for some reason, it's not really catching on here in California. In fact, only for California, whose population is 12.1% of the country's, we only see about 2.3% of the ground source heat pump activity, and that's a quote directly from Project Negatherm, which was a project sponsored by the California Energy Commission. Over 1.5 million geoheat pumps have been installed in both the United States and Canada, but fortunately not too many in California yet. And if you do math, that ends up being 34,500 heat pumps in California. This is the main reason most people install geoheat pumps, the efficiency. Of performance is defined as the heat delivered in kilowatts divided by the power supplied, also in kilowatts. For every 1 kilowatt of energy purchased from the utility, 4 times that input is delivered to a building in the form of heat energy, also, in kilowatts. This magnification of the original 1 kilowatt of energy purchased is due to the heat being extracted from the earth, shown here, the pump thermodynamic cycle, and the direct application of both fan and compressor energy into the water or air distribution system. Next, let's talk a little bit about energy efficient cooling. When we talk about geoheat pumps and cooling, we use the term energy efficiency ratio, or EERs. EER is defined as the ratio of cooling provided in BTUs per hour divided the power required or purchased in kilowatts. C, or energy efficiency ratio, are air source heat pumps and air conditioners and should never be used when referring to water source equipment. EER may be used to compare systems in 2 different ways. You can get the standard rating conditions of different geoheat pumps. This is a way to compare 2 different brands, geoheat pump 1, geoheat pump 2, basically comparing the boxes. For efficiency, heating efficiency, the geoheat pumps are rated at 32 degrees Fahrenheit entering water temperature to that heat pump. And for cooling efficiency, they are rated at 77 degrees Fahrenheit entering water temperature to the heat pump. The second way to use EERs is to determine the overall system efficiency of a geothermal heat pump system at different design conditions. The design conditions are determined by the project location and the design engineer. For example, in Sacramento, the heating efficiency of the entire system, heat pump, fan, would be determined at 45 degrees in water temperature. For cooling efficiency in Sacramento, we would use the design temperature of 90 degrees. If an hour or 8760 analysis is performed for a particular building, this information, along with the system efficiency calculations for all varying entering water temperatures between 35 and the 90 degrees, may be determined. This information may then be compared to a similar bin or 8760 analysis for an air source heat pump or even a central plant system. The known on this slide are the ER and COP values for a split geo heat pump as required to comply with Energy Star for tax credits or other incentives. And typically, Energy Star is more of a residential program, just as an FYI. The ER and COP values shown for Energy Star are standard rating or test condition, which is that first case I spoke about. The ER target of 12.0 referenced above in the slide is from that blue book, and it is for the overall system efficiency at maximum entering design temperatures, and referenced at the bottom of the slide as well. So both blue book and ASHRAE have this recommendation for target efficiency. When we rate water-to-air geo heat pumps, we don't use the same testing standard as air source heat pumps. This is frustrating to engineers and to contractors alike because we like to be able to provide a comparison of different HVAC system types to our clients. The approach outlined in the previous slide is a way to break down the system performance by outside air temperature for air source equipment and entering water temperatures for the water source equipment, so two dissimilar types of systems may be compared for the same project. A more rigorous version of this analysis would be a detailed life cycle cost analysis, where you'd also take into account maintenance and cost of energy. For heat pumps, 3 different testing conditions are performed under ARI, ISO, ASHRAE, ANSI 13256-1. Say that 3 times fast. You'll see those different conditions on your screen. The first column here talks to water loop heat pump efficiencies. Ratings are primarily for a water source heat pump system, which is typically tied to a boiler and a tower, more of a conventional water source heat pump. The second column here, groundwater heat pump, is referring to a water well or an open loop type system. This third column here, ground loop heat pump, that's closed loop geothermal heat pump connection. Note that the entering water temperatures and flow rates vary for each test condition, and so you need to be very careful to note that when you're doing your engineering calculations. Finally, I'd like to also mention that in addition to this standard for the water-to-air equipment, there is an ARI, ISO, ASHRAE, ANSI 13256-2 that provides standard testing conditions for water-to-water geo heat pumps. Okay. As previously, the standard rating condition for geo heat pumps in heating mode is at 32 degrees Fahrenheit entering water temperature. At temperature and a given flow rate, we are given both the heating capacity and the COP values by the manufacturer. Sub P, which I've shown here in red, is the energy in watts consumed by the system for pumping energy. No correction to the standard rating values is required for pumping as depicted in this slide. The watt energy for pumps has already been included. However, it is only for the amount of pump energy required to overcome the pressure drop through the water coil in the geo heat pump. F is the energy in watts consumed by the geo heat pump for energy at design conditions. The external static pressure of the ductwork is not accounted for in the standard rating values. This must be corrected applying the calculation shown here. So here in the correction value where it says fan static, you would insert your ductwork design measure such as 0.70 ESP. That's the number that you need to insert here. When correcting for the fan energy, it is important to note that this additional energy in the form of heat is applied and actually increases our heat pump capacity, as noted here by the plus symbol. Since accounting for the additional watts required for this fan energy to overcome the static pressure of a ducted system, this also results in a corrected COP value less than the stated value for standard rating conditions by the manufacturer. So you have the watt of the heat pump compressor and the fan, and with that correction, you will get a little bit different number than what is in the published data. We need to make these same corrections. Note that for cooling applications, the fan energy, which is W sub F, adds heat, which reduces the stated cooling capacity of the heat pump. And you'll see that here denoted by the minus sign in the corrected capacity calculation. Correcting for this fan energy, just like heating, will reduce the EE or efficiency rating of the heat pump in cooling mode. So again, we need to correct our values here, very much the same as what we did in the previous slide. And again, this is standard rating conditions, so we do not need to do anything with the pump energy. That's already accounted for. Now, we want to look at that second case where we're actually comparing a real project at design conditions. We want to correct for design conditions, and it's really important at this point to speak with the heat pump manufacturer about what is and is not included in their performance data. In this particular example, you'll see that there's a lot of really good information here. We've got entering water temperatures, we have different flow rates and pressure drops, we have heating conditions, cooling conditions, and we have various performance data here that we can work with. In this particular example, the design data includes a small static pressure value for the fan, and no static pressure budget for the Geo heat pump up to 2 tons, but it does include a 0.2 ESP for heat pumps in the 3 to ton capacity size. Corrections need to be made to account for the incremental static pressure not provided in the performance data provided here. And you would apply the same or similar calculations that were shown previously for standard rating conditions. So in this particular unit, there is also no accounting for pumping energy. So to accurately portray the performance of this particular heat pump at design condition, corrections will need to be made for both the additional fan energy by the ductwork and for the pumping energy. In addition to these heat pump system components, the more additional corrections for airflow, water flow, and building temperatures must be made. Note up here in cooling mode that the entering air temperature condition is at 80-67, and that's not typically where most of our buildings will be performing or be required to perform. Note that similar corrections will also need to be made with the air source equipment. This is not unique to geothermal heat pumps. It is important to understand what is and is not included in the efficiency ratings of all types of mechanical equipment, especially if a feasibility study or life cycle cost analysis is being prepared. So I've reached the end of my presentation. Before we open it up for questions, I'd like to leave you with a few of these takeaways. Geo heat pumps provide the most efficient method of heating and cooling a building. I think we all understand that. Geo heat pumps are both renewable and energy efficient technology. This is one of our challenges, especially here in California, recognition by some of the independently owned utilities to put the geothermal heat pump into both of these categories. Utility perspective, Geo heat pumps reduce utility peaks and improve load factor, something we direly need here in California. As I alluded to in my very first slide, Geo heat pumps are one of the strategies needed to meet California's net zero energy goals. And there is no question, they do work here in California. Thank you.
Thanks, Lisa. There's information on the screen. If you have any questions after the presentation, feel free to email info@californiageo.org. And note that there will be a post-webinar survey sent out via email to you, and we welcome any comments, constructive, that you can possibly offer to help us with future presentation and to get more information, better information out to you. You can lower right corner, the CaliforniaGeo website, california.org. There's a contact phone number with any questions. We want to offer ourselves as a resource to the industry, so feel free to contact us anytime. Once scrolling to the top of the screen, see a toolbar or a taskbar that pops down with participants as well as a chat feature. By clicking on one of those, opens up a side window that you can use the raise hand feature in the participants list, or you can use the chat feature. And at the bottom of that chat box, you'll see the area to type in. Want to open to any questions, comments, anybody out in the field? I think this was a wonderful presentation, really in-depth for Geo 101 with some important information for everybody in the industry, both building and design. At this point, we'll welcome any questions, comments, applications. Okay, one, excellent info. One of the slides, the components were shown. In the left-hand part of the slide, it looked like colored pellets. What's that? If you're talking about the polyethylene, high-density polyethylene slide, where there were different colored pellets, and that is the polyethylene. That's the I guess the ingredients, the initial ingredients that they start with to create the pipe. And again, gas lines. If you're familiar with those gas line installations, those are usually a yellow. So they start with a yellow resin or yellow pellets. For theirs, ours is black. That's what we typically throughout the industry is that black pipe. But just the materials, as Lisa scans to that, that you'll see off to the left, that are formed into the high-density polyethylene. One of the notes on that polyethylene is that typically it has a 50 to 55-year warranty once it's in the ground. And the sixth bullet point on that is you can stretch wood of that high-density polyethylene feet before you see any failure. And the fusions of the pipe are actually stronger than the pipe itself. So it's very durable. But those pellets are the virgin form of the pipe being made. Great, thank you. Comment, concerns, again, using the chat feature or the raise hand feature. Thank you. I'm going to